Okay, so this will be our last lecture on Stein stuff. Next week you'll have active learning, and then Larry giving you how he feels about assumptions in the theory, and that'll end off the course. So I just wanted to recap what we finished on last time. This is what we call Stein's paradox, and the setting was if we had D independent normal observations, and they had unrelated means, right? Mu1 through mu d are completely arbitrary, and D was at least 3. Then we saw that this very simple estimate, which we call the James-Stein estimator, where for each component of this is going to be an estimate of the corresponding component of the mean. So the first component of this will estimate mu1, and so on and so forth. We just take the data, right, x, and we shrink it towards 0 by this amount, 1 minus d minus 2 over the norm of x squared. So the interesting thing here is you see that actually our estimate for, say, mu1, which is given by the first component, depends on not only x1, but also x2 through xd. So these completely unrelated, statistically independent observations are informing our estimate of that mean. And we're estimating mu1 with information from x1, but also all the rest. It's called the James-Stein estimator. And we actually proved, using Stein's lemma, that this thing dominates the identity estimator, which is just taking x1 to estimate mu1, x2 to estimate mu2, and so forth. Right, so it's pretty mind-blowing in some sense. But then, now that you've seen regularization for, I don't know how many years of your PhD, you'll see it almost pop up in every course you take on ML and statistics. You can think of this as the idea that this is an unbiased estimate, right? Certainly the expected value of this gives us the means exactly. This is biased, but it has lower variance. So this is a very concrete example of where shrinkage, it plays with the bias variance trade-off in such a way that actually this thing has better mean squared error than this for every possible underlying parameter mu. That's what it means by dominate. It means it has at least as good risk for every mu, and for some mu it has strictly better risk. So we proved that last time using Stein's lemma. That was one nice application of Stein's lemma. If you are looking for a challenge, try to explain this to your parents, presuming that your parents aren't statisticians. Try to explain this to someone. It'll be good practice to see whether you really can explain what it is you're learning in your PhD. And give an example like the one we gave in class. And here's an interesting side note. Mu hat James-Stein positive part, this guy, where we actually just take this shrinkage factor and we truncate it at 0. So this could be positive or negative, right? If the norm of x squared was small enough, then this whole term could be negative. So we actually could be moving our observations through 0 to form the estimate of the means. Well, that seems like a bad idea, right? So let's just truncate at 0. If this is ever a negative, let's call the shrinkage factor 0. That's just called the positive part James-Stein. That actually dominates James-Stein. So somebody asked me last time, our admissible estimators, I don't remember what the question was, but being admissible, the point is not itself a holy property. Or rather, if the identity estimator is dominated by something else, this thing itself can be dominated by something else in turn, right? It's not like it's not like we can say that this thing dominates the identity estimator, and so it's the one we should go with. This is an example of an estimate that actually dominates its mean squared error. And this, I think, was immediate after James-Stein wrote this paper. I think it was 1956 this paper was written. This was very immediately after realized to dominate the James-Stein estimator. And then it took people almost, I think, 30 years until 1991 or sometime in the 90s where they discovered an estimator that actually dominated this one. It's by Shao and Stratterman. They have an estimator that dominates the positive part James-Stein. And that one's much more complicated. So, I'm not sure. I actually don't know if there's something that's been proven to dominate that one. I know there's no proof that there exists an inadmissible estimator when, Yeah, an inadmissible estimator when d is bigger than or equal to 3. We don't know whether there's an estimator that cannot be dominated. That has not been proved yet. Okay, but the gains are kind of marginal. So at some point it may just seem more like a mathematical exercise than something practical. Any questions about the Stein estimator? I'm just going to leave it at that unless there's more questions. Well, maybe we'll hear a little bit more about it from one of the course projects. Okay, so today we're going to talk about two applications of Stein's lemma. One that is a way to compute divergence in a tricky situation. Another that's a way to use the divergence we computed to get a uniform bound between Stein's unbiased risk estimate and the true risk. So we're going to go through both of them fairly quickly. And the details are in the notes, but I figured it's worth seeing both, because each of them touch upon something you've learned in this class already. So the first one we're going to do is the divergence calculation. So we're going to compute the divergence for the lasso estimator. And you're going to see it actually gives us something a bit surprising. Remember, divergence is, we can think about it as it gives us an unbiased estimate for the degrees of freedom. So it's going to tell us the effective number of parameters that are being used by the lasso. But Stein told us that that also can serve as an unbiased estimate for the optimism, basically, the difference between training and test errors, so that we can use this divergence to get an unbiased estimate of the risk. So at the end of the day, we'll have if you ever solve a lasso problem, we can write down something we can actually evaluate in practice whose expectation is equal to the risk. Okay, so this was, just to remind you, this was the lasso problem. The reason I chose this example was that it was hard enough that it's not something that you could maybe do in a homework. Like you could do I think we even in the homework or even on the midterm, I can't remember, we computed the divergence of like a linear smoother. Right, if y hat was, or yes, an notation here, if mu hat was s times y, then we saw that divergence, which is the sum of the partial derivatives of mu hat with respect to yi, was just equal to the trace of s. Right, you can just see that right from differentiation. So there's a bunch of examples we can do like this that are fairly simple. This is an example that's harder, so it'd be nice to go through and lecture. And it also uses some of the kind of tricks with duality and the KKT conditions that we hinted at earlier in this class. So this is the lasso estimator. X is our predictor matrix, y is our response. This is our tuning parameter. And we're going to be in a setting where we think of lambda as fixed. So we're just interested in solving the lasso problem at some fixed value of lambda. And we're going to try to compute the Schur there. And so if we wanted to choose lambda, we could do this at many different values of lambda. Get a Stein's unbiased risk estimate for every value of lambda. Okay, and as we did in the last lecture, we're going to assume that y is normal with mean mu and variance sigma squared I. So nobody really questioned me. I mean, I guess I didn't really leave a pause for a question, but people never really asked about this particular distributional assumption when we compute the divergence. Of course, we saw that the Stein equation was specific to the normal distribution. Remember when we motivated degrees of freedom, we didn't actually assume normality. All we had to assume was that the points that we're observing were uncorrelated. So it's much weaker. Here we're in a setting where we're actually assuming that the errors are normal, not that they're independent. They're normal, which is even farther from what we might want to believe in practice. But when we do that, we have a kind of a more refined mathematical tool at our disposal. So it's a trade-off. So how do we compute the divergence of this guy? So we're going to solve the lasso problem. It's going to give us beta hat. And to estimate the mean, we're going to take x beta hat. Right? We're not actually assuming that the true mean is linear. But of course, if we're going to fit a sparse linear model, our estimate of the mean is going to be x times the estimated coefficients. So the first thing we have to do is compute it. Well, actually, the only thing we're going to do in this example is compute its divergence. How do we do that? That's going to be our task. Well, before we compute its divergence, we have to even check that this is a kind of worthy goal to pursue, because in order to apply Stein's unbiased risk estimate, remember we need to know that the function, thinking this is a function of the data y, so this function of y, so mu hat of y, has to be almost differentiable. Right? That was a precondition we needed in order for the divergence to be equal to the optimism in expected value. Otherwise, Stein's lemma doesn't go through. And remember, you can see that we needed that when we actually did the proof. We needed to basically take the integral of f prime between two different endpoints and declare that was equal to the difference in the function at the endpoints. So we needed to have something like absolute continuity. So how do we check that that's true here? That's what we have to do before we even compute the divergence. So here's a question that we may ask ourselves. How do we know that the lasso fit is even continuous as a function of y? Forget about almost differentiable. How do we know it's even continuous? Right? Absolute continuity means that it's continuous and has a derivative almost everywhere. It may actually seem a bit surprising that it's continuous. Think about it like this. If I take y and I move y around a bit, then the active set might change. Right? We know that the lasso solution we know is equal to x times only over the variables that are active, so selecting out the variables that happen to have a non-zero coefficient times our estimate for those coefficients. And we saw from our work on the KKT conditions that that actually looks like this. So it's basically given by doing regression on y and then applying some kind of shrinkage to those coefficients. That's something we derived. A here is a function of y. What variables the lasso finds obviously depends on y. So if I took y and I moved it a bit, it's perfectly believable that A might change. Right? It might look, if I move y a bit, like this active set's more desirable than this one. So if this changes, then we're kind of doing regression on a different subset of variables. And if we didn't have the shrinkage term, then if the subset of variables changed and we did regression on a different set of variables, then the fit wouldn't be continuous. And if I was able to move y and all of a sudden variable 5 disappears from the active set and variable 7 comes in, the regression coefficients would look different. And so it would actually be discontinuous. So the only hope we can have that the lasso is actually continuous as a function of y is if some very magical property happened where the shrinkage is such that as I changed y, whatever variable was going to leave the active set, this shrinkage term was pushing its coefficient to 0. Right? We want to be that if I moved y in such a way that as I kept moving it, it looks like variable 5 would disappear. The coefficient of variable 5 is already getting smaller and smaller along that direction. At the time we kick it out, its coefficient is already 0. And at the time we introduce something else, that thing's coefficient is 0 and then gets big. That's maybe the only way we can imagine that this kind of complicated function of the data is continuous. And the first attempts to prove that the lasso fit is continuous actually went through this kind of analysis. It's extremely intricate, right, to try to prove that. We're going to see that if we just use the lasso dual, the proof that it's continuous as a function of y is like one line. And in fact, it mirrors what you did on your homework already. And we might have even seen it in the KKT lecture. So basically, it gives us the conditions we need in order to apply Stein's lemma without any work. And it comes from writing down its dual problem, which I'm going to skip because we did it in the KKT condition lecture and you did it on this homework. Or you're doing it, I guess, on the current homework for a slightly different problem, not the same one. The arguments are similar. So that's the lasso dual. Okay, and we know furthermore that actually x beta hat is given by y minus u hat from the KKT conditions. Well, let's look at this one. As a function of y, u hat, repeating what we had said before, is the projection of y onto some set C. It's the closest point u to y among all points that satisfy this condition. This condition we'll write as the set C. C is the set of all u such that the maximum absolute entry of x transpose u is less than or equal to lambda. That's actually it's a polyhedron, convex polyhedron. So that might be the set C. And here's y, and that's u hat. X beta hat, we know the lasso fit's actually the residual. It's what we get when we subtract u from y. So it's this part. So first of all, we can observe that the projection onto a convex set is actually a non-expansive map. And I didn't have you prove that in the homework, but if you're taking the convex course, for example, that might be something you would try to do as a good exercise. It's not hard to prove. Projection onto a convex set is non-expansive, which means that if I ever have the projection of a point y onto the convex set, which will write u hat of y, and I subtract off the projection of another point, call it y prime, onto the convex set, and we ask for the distance between them, that's bounded by the distance between the 2 points originally. So just draw yourself this picture, right? If I have another point, say, up here, and that's y prime, and I ask for the distance between their projections onto the convex set, this would be u hat and u hat prime. It can never be farther away than the points were originally. Convexity is a super important property here. Right? It's not true about sets in general. So think about this set. Right? What's the projection? Say, what's the projection of these 2 points onto that set? It's here and here. Those 2 points are farther away from where they were originally. So convexity makes this true. So it makes this fact true. OK, so this tells us actually that the dual solution is a Lipschitz function of y with Lipschitz constant 1. In fact, the exact same thing is going to be true about the residual as well. It's going to be Lipschitz with constant 1. You can get it from another picture like this. But even if all you knew was this fact, you can prove that it's Lipschitz with constant 2, right? Because if you subtract x beta hat and under y and under y prime, then you just get it's y minus u hat minus y prime minus u hat prime. And the triangle inequality will tell you that's at most 2 times y minus y prime. So in any case, this is a Lipschitz function. That's what we learned from the dual, without having to go through any kind of hard math. If it's Lipschitz, it immediately applies as continuous. So continuity we get automatically. So actually, this does happen for the lasso, this property we talked about with the coefficient shrinking to 0. Just that we didn't prove it that way. We proved it some other way. And it's also almost differentiable. The Lipschitz function is differentiable almost everywhere. That's not the same thing as almost differentiable. The way we define almost differentiable, you would think that it has to mean differentiable almost everywhere. But the way Stein defined it actually is not quite the same thing, although being Lipschitz is good enough to imply it. That's a result that's called Rademacher's theorem. It's the same Rademacher that you learned with Rademacher complexity. He's a productive guy. So Lipschitz implies both those conditions. We didn't have to do any hard math. We just saw this picture, and then we opened up maybe our textbook on real analysis to get those. So basically, it tells us that computing the divergence is a worthy goal, because once we compute it, we can then adjust the training error of the lasso to get an estimate for its risk, unbiased estimate for its risk. OK, now we're going to do the divergence calculation. And you'll see that this perspective is actually basically where we get the answer again. It's really the same picture that's going to give us the answer. Any questions before I do the divergence calculation. And then just draw the picture bigger so that we can get a sense for it. So there's another thing that's true about the primal dual relationship, other than what I wrote down, and that's the nature of what each of these faces represents. So the lasso dual, we know, is the projection of the point y onto this set C. This set C is the set of all u such that x transpose u is less than or equal to lambda. It turns out, which I think you might be able to buy just by intuition, that each of the faces of this polyhedron corresponds to some number of x's that are exactly equal to plus or minus lambda. Okay, so if I just look at this face is in one-to-one correspondence with a set A that has the property that xi transpose u is equal to lambda for all I in the set A, and xi transpose u in absolute value is strictly less than lambda for all I not in the set A. Now, you can believe that because this polyhedron is the intersection of a bunch of half spaces. At one of the faces, we're going to be we're going to lie on some of those half spaces in the sense that some of these constraints are going to be tight. We're not going to be strictly in the interior if we're at one of these faces. And each face has a different defining set of variables for which it's tight. In fact, really, it also defines the set of signs. So it's equal to Si times lambda, right? Because it's telling us not only we're on a boundary, but which one we're on, plus or minus. So each of these faces is in one-to-one correspondence with a set A, which is some subset of 1 through P, a pair, A and signs, a set of signs which is a subset of sign vectors of length size of A. I haven't told you what A and S A are. They're just, each of these just correspond to some A and S A on the boundary of the polyhedron. Okay, hopefully that makes sense. Here's an interesting question, just to test your intuition. Is it true that for every possible set of subsets of 1 through P and every possible sign combinations, there is a face? So we said that every face does correspond to some set in some subset. That's just because this thing is right, we can write this as it's the intersection over all u such that xi transpose u is less than or equal to lambda, and xi transpose u is also bigger than or equal to minus lambda. But is it true that for every subset I can find a face? You say no. Why do you think no? Well, so they can't be parallel, right? Because they all go through 0. Actually, that's not true. These don't go through 0. So yeah, if they're both parallel, let's see if that can happen here. Yeah, right.
That will happen if there is linear dependence, right?
So that, you're right. They could be parallel. For example, if I took xi and then I took xi over 2 as two different columns of x. So yeah, that's a good example. If I have two parallel lines, then and I ask for the intersection of the half space generated by both of them, only the one on the inside, say, is going to matter. And more generally, there's actually this very interesting, if you guys are interested in this kind of thing, in computational geometry, they study something like if I take a box. So let's suppose I'm in RP now. This is the primal dual picture. This is an Rn, and that's an RP. Let's take the unit box in RP. So it's the set of all vectors, we'll call it V, such that Vi is less than or equal to lambda, and Vi is bigger than or equal to minus lambda. This is this box. So really, every possible subset of 1 through P and every possible sign combination appears on one of the faces of this box, by definition. Right? You pick out 1, 3, 5, and signs minus 1, 1, and minus 1, then that's going to correspond to a particular face on this box. What this is actually, the set here, C, where it's actually generated, if you think about it, it's actually generated by taking this box in RP and applying a linear transformation to it that goes from RP to Rn. And that linear transformation, it's actually the inverse image under a linear transformation. So there's often confusion here. I don't mean X transpose inverse, like the matrix inverse. I actually mean the inverse image under the linear map X transpose. That's by definition what this is. It's the set of all points U such that their image under the linear map X transpose lies in the set, whatever you want to call this set, D. So C is equal to the inverse image of D under the linear map X transpose. So it turns out I can think about the inverse image of linear maps and linear maps as on par. They're not really that different. You can think about this. There's another linear map that's being applied in some sense. And there's very interesting work in computational geometry that says that if you take a polyhedron in one space and you multiply it by a linear transformation down to a space of lower dimension, let's suppose P is bigger than n, then you're going to lose some faces. Some of the faces of this polyhedron are not going to appear in that one. They're actually going to get pushed to the inside. And it's a very interesting property that they have very strong statements about. And what that's telling us, essentially, even without the kind of example that Kevin gave, is that generically, if we have P larger than n, then there are just going to be some combinations of sets A and SA that can appear on the face of this polyhedron. And why that's interesting is that, well, I haven't told you yet what these correspond to yet in terms of the lasso solution, but you can guess what they are based on the notation. If I take a point y and happens to project to this face, that face corresponds to some set A and some subset of signs SA. It turns out that the active set at y is A, and the signs are SA. That you can also see right from the KKT conditions. I didn't decide. I'm not going to spend time on it now, but it's in the notes, and the notes reference papers that kind of prove all this. Okay, you can really just see it from here, actually. When we wrote on the KKT conditions, there was two conditions. The first was that y minus u is equal to x beta. The second was that x transpose u is lambda times the subgradient of the L1 norm at beta. So this is saying that the subgradient is strictly less than 1, which is implying that beta hat I is going to be 0 at the solution, at whatever the u is that projects here. Okay, but that's maybe slightly more details than we need to get for just the high-level picture. The high-level picture is that if you happen to project y to this face, it has active set A and signs SA. That's guaranteed. So same will be true about this y. This is not an orthogonal projection. I don't know why I drew those like that. But whatever y's we happen to observe, if they project to the same face, they will have the same active set and signs of the lasso solution. That comes from this duality picture. And the interesting thing I was trying to get to here was that because some faces don't appear, some active set and some signs don't appear on the boundary of this polyhedron, it means that some active sets and signs aren't achievable by any lasso estimators, no matter what y is. Right? maybe there was a face that corresponded to 1, 3, 5 with signs -1, -1, and -1. And when we took this linear map, it got pushed into the inside. So it doesn't appear as a face anymore. It means that actually, no matter what y is, you could try your hardest to find a y that gave you that active set in signs. You're not going to be able to do that because it's not going to appear as a face of this polyhedron. So some interesting kind of perspective on how the lasso chooses variables comes from duality. And I claim actually that all this rambling that I just did was for interest's sake, but we've already proved the divergence calculation, which is that if I take y and I move it around a bit, then for almost every y, let's suppose I take this y, if I move it around a bit, it's going to have the same active set and signs. The active set and signs are going to be locally constant. Because here, I move it around, say, in this ball, every point in that ball is still going to project to the same face. I just told you the active set and signs are determined by the face, so they're locally constant. That's true here. It's true here. It's true here. Right, if I take any of these balls and I try to project them onto the polyhedron, they're all going to project to the same face. So the active set and signs are going to be locally constant. Where is it not true? It's going to be not true in some places. Right. So it's going to be true, say, along these surfaces. These are actually what we call the boundary of the normal fan for this polyhedron. Maybe it sounds exotic, but it just means that if we are here and we move to one side, we'll project onto this face. If we move to another side, we'll project onto a different face. In this picture, it's a bit misleading because this vertex is actually a different face than this edge in 2D. Okay, so if we're here, we're going to project to this. And if we're here, we're going to project to that. So actually, if we move a bit from one side to the other, the active set will change. But that's only true along these lines. You can tell from the picture that these lines, they look like they have measure 0, right? And in general, you can think about it, if I have some big polyhedron, these are the boundaries of some kind of well, they're boundaries of something, and boundaries of anything are going to have one lower dimension, essentially. So they're always going to be a set of measure 0. So what we've just proved by talking, and it's in the, I put some of it in the notes, and you can take a look at the papers, but that for almost every y, we've proved that A and S are locally constant. They don't change as we change y. What does that mean? It means if we take a derivative, we can treat them as constants almost everywhere. That's literally what it means. So for almost every y, we can take partial derivatives in this expression and treat A and SA as constants. There is a set of y for which that's not valid. That's the set of rays that I drew on the board. Those have measure 0. Eventually, we're going to take an expectation of our divergence. So we don't care what happens on sets of measure 0. So there we go. Just take a derivative with respect to y and treat A and SA as constants, which you may have done without even thinking as your first attempt, right, to derive the divergence. You may have just taken a derivative with respect to y and ignored all the other quantities. Turns out that's actually going to be correct. So the partial derivative of, let's call it x beta hat, and the ith component with respect to y, and we sum it up. Well, that's just going to be, this is going to go away, because we're treating it like a constant, which we can. This is just some matrix. And we can treat A as a constant, so it's just a trace of that matrix. So do trace rotation, you're going to see this is equal to just the trace of the identity matrix of dimension A. So it's actually just the size of A. And that's it. That's the calculation. It's very easy to do in practice now, right? We get a lasso estimate. It returns to us 9 variables it selected. It did select them adaptively, but our calculation for the divergence is going to be 9. And we're guaranteed that if I take the expectation of this, it's really going to give me the degrees of freedom. So the degrees of freedom in the lasso is the expected number of variables that it selected. And for our purposes, the sure estimate, Stein's unbiased risk estimate, is just going to be equal to, this constant term which is always there, plus the training error plus 2 times sigma squared times the number of variables the lasso selected. This is sure. And it has the property now that if I take its expectation, it is the risk. It equals the risk. Questions about that calculation? Kevin? In order for this to be what we put here, that depends on normality. So we've proved that for any estimator, the unbiased estimate of its risk is training error plus this plus its divergence. That depends on normality. Is that surprising? Is this result surprising, or is it intuitive? What do you guys think? It's saying that the expected number of parameters used by the lasso is just the number of parameters used by the lasso is just the expected number of things it found. In other words, if I want to adjust its risk, then I have to just add, if it finds k variables and I want to adjust its risk, I take its training error and I add something that scales with k. Well, what else? What other procedures have things that I add with k? It's like linear regression, right? Linear regression on k variables would be having degrees of freedom k. So the optimism, the difference between their training error and test error, would be 2 sigma squared k. Same is true about the lasso. Is that surprising, or is that intuitive? What happens if I gave you these variables ahead of time? I said, here's A. I'm going to fix it. Do regression on them. I know these variables are good. Ignore the rest. Then we would actually be putting size of A here, right? That's just doing linear regression. So the difference between its tests and training errors is the size of A. But that's not what we're doing with the lasso. The lasso is actually finding A. No one's telling it what the right variables are. So how come it has the same optimism? Same degrees of freedom. That's, I think, quite surprising. So when people first looked at these results, they seemed wrong. They didn't seem right, because they actually seemed to counteract, or they seem to contradict the fact that the lasso is doing things adaptively. Well, the kind of right intuition is that, yes, the degrees of freedom is still the size of A, or the optimism is still like this. But the reason that it's able to get away with this is because it actually shrinks the coefficients of those variables. So the optimism is automatically not as bad because of shrinkage. If we did least squares on A, the training error is going to look even smaller than what the training error would look if lasso had found A, because we know that it actually doesn't fit the variables as aggressively as least squares. So it's doing two things. It's finding the variables adaptively, and we're thinking that's probably going to make it to have more covariance, more effective parameters than linear regression would. But then it's being less aggressive with the way it's fitting them. So there's a surplus kind of degrees of freedom in searching for the right model. Then there's a deficit that comes from shrinking. We save a little bit. And the kind of magical property is that it comes out to be just the number of expected parameters for the lasso. Right? So shrinkage is saving us in some way. If you were to compute this for best subset selection, it would be bigger than A. Because it finds the variables and then it does regression. And in fact, you can, did we have this on the homework? We might have had this in the homework for the orthogonal case. Is that, I think that might be true. In any case, you can, in some examples, you can see this can be, actually with subset selection, it can be arbitrarily large. This can be 10 times A in some examples. So you don't have the same kind of optimism control. OK. Any questions about that? Questions about how you would use this result? You would now, at every value of lambda that you're interested in, say you put down 100 values of lambda, you'd solve the lasso problem. You'd write down the training error. You'd record the number of active variables. And you'd form this statistic, r hat. And you'd minimize that statistic over all the choices of lambda. That would be one way to choose lambda. That would be using sure for the purposes of model selection, choosing lambda hat to minimize r hat. And that's going to get at our next part of the lecture. OK, so in order for that to be good, we have to have the property that somehow this over lambda concentrates around its expectation. Because at any fixed lambda, its expectation is the true risk. If it's true uniformly over all lambda, then we'd be comfortable with minimizing it and claim that at the random choice of parameter we found, it's still close to its expectation. So whatever the thing that came out of this is still going to be close to its risk. Unfortunately, that's very hard to do for the lasso, say. I don't think, I could be mistaken, but I'm pretty sure people haven't done that. It's, like I mentioned last time, it's just really hard to do for all of the modern procedures. Because how these behave with, say, over lambda is eludes us in terms of our understanding. But I'm going to give you an example of something that's still kind of of practical interest where we can do it. So then we'll finish with that. Let's take a break before I get to that. You guys are looking tired. I think it was probably also a hard topic. But let's take a quick break. This, by the way, I think this is a very cool result to put it in context. The way this was used at the time was that Donahoe and Johnstone, we've already talked about them a bit when we talked about non-parametric regression. This is where they did this work in that context. So they studied wavelets, and they have this nice result that we talked about already that says that wavelets achieve the minimax rate of convergence over a very broad class of functions. And so in some sense, they outperform other competitors, like smoothing splines, for example. All these results, right, all these results that we learned in non-parametric regression, density estimation, actually, everything we've learned so far, if you look, it says if lambda is equal to this, then we get this nice rate. That value of lambda, say, suppose we're talking about wavelets, or lambda for the lasso, or whatever, it depends on unknown quantities. It's not something we can ever use in practice. So it depends on things like sigma squared. It depends on properties of the true signal in many instances as well. And it depends on, and for wavelets, it's going to depend on things like the smoothness of the assumed function. You remember for kernel smoothing, the bandwidth depended on things that we didn't know. We had like an asymptotic scaling for it, but the exact thing we should plug in, we can't ever do in practice. So this is the first example that I know of this calculation leads to the first example I know of an estimator that's fully data dependent. So the tuning parameter is being chosen by Schur. And these authors prove that if you do that and you plug it in, then you still get a minimax estimator. So wavelet smoothing with the threshold selected by Schur is still minimax. I think it's a very satisfying result. There's nothing that's being swept under the rug in terms of, well, if you select the tuning parameter right, then you'll get the fast rate. And we're just going to do part of that proof. obviously the result is a long proof. We're going to prove the part about sure. So what's soft thresholding? To remind you, it's what I get when I take y, and I compare it to a level lambda, and I just, in every component, I either subtract off lambda if y is bigger than lambda, I set it equal to 0, or I add lambda to it. That's the soft thresholding operator, and we can think about it like it's the solution to a lasso problem when the design is identity. For wavelets, just so you can keep it in mind, we actually apply soft thresholding to something like W transpose y. We compute the wavelet coefficients, which are given by W transpose y. We soft threshold them, and then we multiply that thing by W, if W is our basis matrix, where each column has a wavelet evaluated over our input points. So that's how we would apply it for wavelets. What is sure here? We're going to assume sigma is 1 so that it's not as, we don't have to carry it around. This is the sure estimator. N minus n sigma squared plus the training error plus, well, it's 2 times sigma squared times the size of the active set, because we actually just proved that for the lasso. The divergence is the size of the active set. This is a special case of the lasso in some sense. And what's the active set here? It's just the number of things that weren't thresholded. So we can just write that as A lambda for now. That's sure. It's very easy to evaluate. And let's just do this first. Let's change this to an n. And write this as n minus the size of the active set. No, as minus. OK, so before I had a minus n, now I have an n minus a 2n, so I didn't change anything. And before I had a 2 times the size of a, and I still have that. So I didn't change anything. I just wrote it like this for some, because it's going to help in the next step. So n stays. This is just the sum of the square differences between yi and its soft thresholded version. So what is that? Well, we can think about 2 cases. What happens if yi happens to be between minus lambda and lambda? Then its soft thresholded version is just 0. So this is just yi squared. So there's going to be some terms that look like yi squared. Right? We could really say it's the sum over all I that were thresholded of yi squared. What happens if yi is either bigger than lambda or it's smaller than minus lambda? And the difference between yi and lambda is just going to be equal, the difference between yi and its soft thresholded version is always going to be lambda. Right, we're just moving away by lambda. So we can think about it like plus another sum, which carries forward lambda squared whenever yi is not thresholded. That's the training error. A more concise way to write that is this. It's just the minimum of yi and lambda squared. You can see that this matches the same expression we wrote down. Handles the 2 cases. And this one, well, these are the number of things that are thresholded. N minus the size of A is the number of things that are thresholded. So I want to put that in the sum just for simplicity. I'll just use an indicator that say yi squared is less than or equal to lambda. So this is sure. We're just writing this now for mathematical convenience, not for computational convenience, just because we want to analyze this as a function of lambda. And in fact, let's put the n in there. So we'll just put a 1, and then we'll have the sum on the outside. That took care of the n. And let's look at r over n. Just because it happens to be a nicer scaling. So everything here should be divided by n. OK, so the average risk over n is equal to 1 over n times this. all right, let's call, I think in the notes I called that. I didn't call that anything so far. Okay, so that's just what it is. What we're interested in is the difference between the Stein's estimate of the risk at lambda and the actual risk at lambda, which happens to be also the expectation of Stein's estimate, right? So let's call this risk over n. We're going to call u hat as a function of lambda. That'll be this whole thing. It's just risk over n. Called it u hat, I guess, for unbiased as a function of lambda. And subtract off little r of lambda, where little r of lambda is just equal to the average risk, true risk. So the expected value of the sum of, you can write it like this, doesn't matter which order I put it in, expected value of the true mean minus our estimate for it. Okay, so this is the risk, the expected value of the mean minus our estimate squared, summed up. I'm looking at the average risk. That's little r of lambda, the top of page 10 in the notes. And this we're going to call, right? So we can actually write this as 1 over n times the sum of all this inside stuff minus this term. We're going to write that as 1 over n times the sum of wi of lambda. We want to prove this thing is close to 0 uniformly over lambda. We've written it as an average of things that we're calling wi, which is wi is just this quantity minus this quantity, the expected value of mu I minus mu I hat squared. Well, wi, let's make some observations about it. Wi are independent. That's one of the kind of advantages to working in this simple setting, is that actually think about the estimate, the soft thresholding estimate. It only depends on yi. It doesn't depend on any other components of y in the ith component. So mu hat I is independent of all the other y's. It only depends on yi. And each of these terms only depend on yi. So each of these w's only depend on yi, so they're independent. Okay, so that's one nice thing about them. That would not be true if we were doing, trying to do this calculation for the lasso, for example. And furthermore, their expectation is 0. Where does that come from? That just comes from Schur, right? That is the property of Stein's unbiased risk estimate. Schur actually tells us that the whole thing has expectation 0, because it tells us that the expectation of the risk is equal to the true risk. The expectation of Schur is equal to the true risk. Actually, in this very simple setting, each one of these things has expectation 0, even moreover. That's because this problem completely separates over I going from 1 through n. We could have asked ourselves to compute the Stein unbiased risk estimate just for mu hat I individually. It would have been this. Just because the problem separates. So this thing itself is an unbiased estimate for the risk at mu I. Okay, so we have independent observations, mean 0, and we're taking an average. We want a tail bound on that thing. We want to make sure this thing is not very far from 0. What's the first thing that comes to mind from your concentration and measure? Well, there's only a few things we learned, right? Lifting is what you would go for, right? So average of, I forgot to tell you one more thing. Probably your you wouldn't know to use Hüfting yet because I didn't tell you this is actually bounded. Now, I'll let that one fly. I'm sure that once I said bounded, you guys would have all said Hüfting. So they're bounded. How do I see that? Well, this thing, well, that's 1. This is no bigger than lambda squared. This is no bigger than minus 2. The whole thing's no bigger than 1 plus lambda squared. And lambda squared, let's assume, I didn't write that down. Let's assume that we're interested in this over some interval, 0 to lambda naught. OK? Well, actually, even with respect to each term, it's already bounded. Bounded has nothing to do with lambda. So you would have been able to see that anyways. And this thing is bounded as well from a simple calculation. So independent, mean 0, bounded observations, use the Hüfting's inequality to get a tail bound for that. So let's do that. Let's just write that out. Hopefully you didn't hope this is familiar, because I picked it so that we can see another application of concentration of measure. So what we know is that the probability that that sum, 1 over n times the sum of wi, which I'm writing as the difference between the thing we're using to estimate the risk, which is u hat, it's Stein's unbiased risk estimate over n, minus the true risk over n. The probability that's bigger than t by the Hüfting inequality. I didn't tell you what the bound was yet. These things are in between. This thing is less than or equal to, let's say, 3 times 1 plus lambda squared. So I got 1 plus lambda squared from here, and you can compute. I did it in the notes. A simple bound on this, which ends up being 2 times 1 plus lambda squared. So the whole thing's bounded by 3 times 1 plus lambda squared. And what does Hüfting's inequality tell us? If we remember from Larry's notes, I actually don't have them in front of me, but so this, I hope I didn't get this wrong. It looks like 2n n squared t squared, is that right, over the sum of bi minus ai squared. Wasn't that right? Or was there an n? Is that right? No, let's see. This should be n squared. Right. OK, so the way I had it in my mind was like this, actually, I think. OK, and so where bi and ai are the individual bounds on each of the terms in the sum, in the average. And for us, this is equal to well, actually, I have a constant wrong in the notes, but it's OK. Doesn't really matter. Each of these is going to be equal to, I have it as 9 times 1 plus lambda squared squared, because I took 3 times 1 plus lambda squared and I squared it. But it actually should be this times 4, right? Because it should have been a 2. So well, I'm going to leave the 9 there because it looked nice for the rest of the analysis. But honestly, it doesn't matter. They're all constants. So you can fix that if you're curious. Epsilon here, or t here, we're going to take to be epsilon over root n. So we're just going to get epsilon. So that's a very good bound from the Hoofding inequality. It tells us that this is very close to the true risk, but what's the problem here? It's pointwise. So this is true for each fixed lambda. What we want to know is that we want the maximum over all lambda that are in some range of u hat lambda minus r of lambda. We want this to be small. So we want some kind of bound like this. The probability this is bigger than or equal to something. Say epsilon over root n is small. So a few observations before we figure out how to fix that. What are we going to take for lambda naught? So it turns out we can't do the calculation over all values of lambda. That won't work. We need to have some upper limit. Well, what upper limit can we choose to make this not very hacky? If you're doing thresholding, what's the largest value of the threshold do you think you might consider? Yeah, that's true. That depends on y, though. We're going to want something that doesn't depend on y. So what happens if all the y's are have mean 0 and they're normal, which we have to assume normality because we're using Stein. Right, so that's hidden down here. All the y's are normal with mean 0, and they all have variance 1, and they're normal. What's going to be the biggest absolute value of y? What is it going to roughly look like? Homework 3, I think. It's root 2 log n. That's what we've proved. The largest value of the largest absolute value of n IID Gaussians with mean 0, say, concentrates around root 2 times sigma times the number of them. So n here. Or sigma times root 2 log n. So sigma is 1. This makes sense here, right? Because if we're going to choose the threshold to be so large, we're going to be declaring everything to be 0. And if everything's 0, then if all the means were 0, say, which is the regime in which we'd be doing this, then this would be the threshold that would kill them all anyways, if lambda was a little bit larger than that anyways. So that's going to be the largest threshold that we're going to look at. Second observation before we figure out how to fix this. What was the way that we went from like the Hoofding or the Bernstein inequality to uniform bounds? What do we use? We use actually VC bounds, right? Or even that sent us on a path where we looked at VC, dimension, Rademacher complexity, and then Larry didn't really talk about it, but entropy and covering numbers are also very commonly used for uniform bounds. I'd be curious if somebody was interested in trying what happens here with those bounds. Turns out there's a very clever strategy that Donahoe and Johnstone used to avoid them. I have a feeling that VC and Rademacher bounds are going to fail because everything here is real valued, and they're usually used for binary valued things. I don't know about entropy, so if somebody's curious, that might be an interesting calculation to try. What Donahoe and Johnstone do is something that's, I think, pretty clever, so I wanted to show it to you so that you might think about it in case you're at a point where suppose you get to a point where you want to prove a uniform bound like this, but you find VC dimension, you forgot it, or maybe you find it too hard. For the example, you couldn't work it out, or all the uniform stuff didn't work out. Here's a way just to use the Hoofding inequality in a clever way to get a uniform bound. And the proof is about it's only another page, but it's a difficult page. So I'm not sure we'll get through in all the last 8 minutes or so, but I'm going to give you the main idea at least. So the first thing we're going to compute is we're going to try to figure out how much these individual terms u and r can vary if we vary lambda from, say, lambda to lambda prime. So maybe we'll skip these calculations because they're not the interesting part. These calculations are just, they just require attention to detail. So the first thing that Donahoe and Johnson do is they say that for lambda that's less than lambda prime, let's let n lambda lambda prime be the number of points I such that basically yi in absolute value is in between lambda and lambda prime. So the number of points we have in between those two thresholds. And they're going to try to get an idea of how different, say, the first term can be. U hat lambda and U hat lambda prime. And everything I'm going to skip here is in the notes. And if you want more detail, you can also go to the paper, which is referenced in the notes. But this ends up being less than or equal to 2 times n lambda lambda prime plus lambda prime squared minus lambda squared. Okay, so that's the calculation that you can do. And furthermore, we have, so this is, I think, a bound on R. We're going to do the same thing with R and R prime. This is less than or equal to, it turns out, 5 times lambda times lambda prime minus lambda. Okay, so why are we doing this? We're going to get some sense for how much these quantities we're trying to bound over lambda are varying over lambda. If we have some idea of that, then that's going to give us a sense of how to do a uniform bound. And this is our idea. This is how they vary with lambda. And so in total, we can say from these two bounds that I don't know why I wrote that in the notes. I should have had u hat lambda prime minus r of lambda prime. So the thing we're trying to bound, how much it varies over lambda and lambda prime, is going to be no more than 2 over n. I guess I missed an n here, times this n, number of things in between lambda and lambda prime. And I have plus 7 times, well, for this lambda, I'm going to take lambda naught. That's an upper bound. And for this, I'm going to call that delta, the difference between lambda and lambda prime. So that's an upper bound of how different that can be. And here's the clever part. This is the part that you should remember, if anything, from this calculation. Once we have that stuff behind us. Which is the following. Let's let lambda j be equal to j times delta, where delta is some number we're going to fix. We're going to just consider gaps of lambda of width delta. So we're going to discretize this continuous interval 0 to lambda naught into points with width delta apart. Turns out taking delta to be about n to the minus 1/4 is what we'll do in the end. But right now we don't know that. We're just going to think about discretizing it. And we're going to look at this event, A, I called it, which is, it's this event that the maximum we care about exceeds, something like epsilon over root n. So the maximum overall lambda between 0 and lambda naught of u hat minus r of lambda exceeds, and the constant here is not important, but you'll see why I took it. I wrote 3 over 3 epsilon over root n. That's the event whose probability we want to bound. We're going to actually break that up into 2 events, and this is, we can actually apply Hüfting on each one. That's where this clever trick comes from, the discretization. We're going to claim this is actually contained in the union of 2 events. The first event I'll call D, I guess, which is that if this is going to, quantity is going to exceed 3 epsilon over root n, then it means that at one of the not points, it would have exceeded, if I take lambda j, one of the points on our discretization, lambda j, it would have exceeded, say, epsilon over root n. Or if that didn't happen, right? Certainly this could have happened. If this didn't happen, then what has to happen in the interval between lambda and lambda j? We have to have that if we look at basically any 1j, and we look at the difference between all lambda around that point lambda j that are within delta, which defines our mesh, then we have to have this being true. Has to be at least 2 epsilon over root n. Right, so this is going to imply this or this. That's where this implication comes from. If it didn't happen, then that we were bigger than epsilon over root n at one of the discretization points, then basically we would have to have, from a discretization points, had left epsilon over root n by an amount that's at least 2 over epsilon over root n to get ourselves to leave by 3 epsilon over root n at some point over the interval. So this is saying something like taking this continuous problem of bounding the process into a sequence of discrete problems, and something about what happens in between the discretization points. What do we do here? This one. We can just use Hüfting here, because these are going to be, we're taking a discrete set. We can actually use Hüfting plus the union bound, right? Because we've chopped it up. So this is taken care of with our current tool set. What are we going to do here? That's where this calculation came in handy. We're going to use the fact that basically we know how much it can vary over an interval of length delta. We wrote it down. And so we're going to basically reduce this. Well, the notes do. We're out of time. The notes reduce this to a tail bound on n, because we actually can control how much this deviates over that interval delta. How do we get a tail bound on n? We use the Hüfting inequality again. In fact, it's just a tail bound on n lambda j and n lambda j plus delta. That's what we end up using. So how many points are in each? Or it's actually n over, this capital N over n. It's an average of indicators, basically, points in that interval. So this is a nice trick. I don't know if there's a name for it. I would call it chunking. Take a continuous problem, turn it into a bunch of discrete ones, solve each discrete problem using your current tool set. For everything in between your discrete problems, use something like a Lipschitz condition or any bounds you can get like this to figure out how much the process can deviate over that interval. If you can control both of those things, then there's no need for something that's fancy like VC theory or Rademacher complexity, et cetera. So we don't have time to go through the rest of the calculations, but I don't think they're particularly interesting. It was more the strategy I wanted to show you. And what we get out of it is that, I'll just write down the punchline, the probability that that's bigger than, well, actually, we get a bound on this in probability. So I'll just write down what the rate is. It's a very fast rate. We just get that, at the end of the day, that using the Hüfting inequality, this thing is stays very close to 0. And in probability, this looks like it's bounded in probability by, it ends up being log n to the power of 3/2 over root n. So it's going to 0 very fast. And that means that if we happen to run Shor, and we happen to pick a parameter value that land in this interval, 0 to root 2 log n, then we could be pretty confident that whatever the Shor estimate of the risk was is close to the true risk because of this work. And that's what makes the wavelet proof go through. All right, that was it for Stein's lemma. You're in for some active learning next week and then a fun lecture, so that's it. Oh, and also make sure to turn in your reviews. Your project reviews, I think, are due tomorrow night. So make sure to do those.